Hello, this is Joseph Sundar from Madras College doing my first year Master of Science in Physics. So let us discuss some problems regarding on Hamiltonian. Problem number 1. Obtain Hamilton's equations for a particle of mass m moving in a plane about a fixed point by an inverse curve force minus k by r square. Hence, obtain the radial equation of motion and show that the angular momentum is constant. So here a particle is moving in a plane about a fixed point by an inverse curve force. So we have to find its radial equation of motion and also we have to show that the angular momentum is constant. In plane polar coordinates, the kinetic energy we are referring it as T and the potential energy V. They are given by kinetic energy T equal to half m into r dot square plus r square into theta dot square and potential energy V equal to minus k by r. So this will be our equation 1. So in Lagrangian we will be adding kinetic energy and potential energy. So therefore it will be L equal to half m into r dot square plus r square into theta dot square plus k by r. So it will be our equation 2. And if we differentiate L with respect to r dot, it will be pr equal to m into r dot or r dot equal to pr by m. So in Hamiltonian equation, we know that the value of h equal to summation I pi qi dot minus L equal to the value of p here is pr r dot plus p theta theta dot minus L. So we are substituting the r dot and theta values in the Hamiltonian equation. So the final equation will be h equal to 1 by 2m. Hence the Hamilton's equations are r dot equal to dou h by dou pr equal to pr by m, p dot r equal to minus dou h by dou r equal to p theta square by mr cube minus k by r square. So this will be our equation 6. And theta dot equal to dou h by dou p theta equal to p theta by mr square and p dot theta equal to minus dou h by dou theta equal to 0. So this will be our equation 7. So from the two equations in equation 6 we have p dot r equal to mr equal to p square theta by mr cube minus k by r square. So this will be our equation 8 and the equation 8 is known as the radial equation of motion. The second equation of equation 7 gives pq equal to constant. So we will take it as equation 9, which is the law of conservation of angular momentum. Since p theta equal to mr square theta, the angular momentum. So we have proved that angular momentum is constant here. So we'll go on to the next question. A mass m is suspended by a massless spring of spring constant k. The suspension point is pulled upwards with a constant acceleration 8 knot. Find the Hamiltonian of the system, Hamilton's equation of motion and the equation of motion. So let us take the vertical axis as z-axis. As the acceleration due to gravity is downwards, taking the net acceleration as g minus a naught. So the potential energy V equal to half k z square plus m into g minus a naught into z. So this will be our equation 1. And the kinetic energy T equal to half m z dot square. So in Lagrangian, L equal to kinetic energy plus potential energy. So L equal to 1 by 2 m z dot square minus 1 by 2 k z square minus m into g minus a naught into z. So if we differentiate this L with respect to z dot, we will be getting pz equal to dou L by dou z dot equal to m z dot or z dot equal to pz by m. And Hamiltonian will be pz z dot minus L, which will be equal to pz square by 2m plus 1 by 2 kz square plus m into g minus a naught into z. So the Hamilton's equations are z dot equal to dou h by dou pz equal to pz by m. So it will be our equation 3. And p dot z equal to minus dou h by dou z equal to minus kz minus m into g minus a naught. So which will be our equation 4. And the equation of motion is z equal to 1 by m p dot z equal to 1 by m minus kz minus m into g minus a naught and mz equal to minus kz minus m into g minus a naught.